operating system. We call that all other disk operating system. We call them Windows and Windows XP and all that other stuff. And though technically they are disk operating systems. So this is the same thing that we have going on here. The original proximity switch was a limit switch, but we don't call that a proximity sensor. We call that a limit switch. So what is basically the category of proximity sensors? You're right, Alexander, but what do we also mean? We mean these are non-contact sensors. So the limit switch is a contact sensor, and then so proximity switches are also non-contact sensors that sense when something is at a certain location, right? So the first one that we're going to look at, and there's some terms in here you're going to have to pick up. There's several things we're going to be measuring according to the data sheets. This shows us an inductive proximity sensor. And what does an inductive proximity sensor detect? Metal. No, just metals. It'll detect most of the metals. They'll detect aluminum. Aluminum is considered to be a non-ferrous metal, right? You understand? So they detect metals. Now, I don't know of any metals that it won't detect. Even copper, it'll detect copper. When we were doing our sensor, when I was getting certified to do sensors, which we don't have the Festo trainer, by the way, but I'm AMP certified. We actually had an analog inductive sensor, and we actually put different metals up there, and we could actually record the output of what it would give you. So these guys sense metals. They don't sense non-metallic targets, but they do sense metallic targets. Then we have capacitive sensors. What does capacitive proximity sensor sense? Yeah, solid. And this is the first basic circuit, a very basic circuit. We'll start off with a proximity, inductive sensor. This is the one. This is the one that we have. We don't have a capacitive here, and it's a two-wire sensor in a solid state. So where does it get its power at? Well, if I hooked it directly across L1 and L2, the first time I activated it would blow it out. We've got we got some over here that none of them are any good anymore, and I guarantee what somebody did across the line. Work. So this is a two-wire sensor. This is I'll say that. And then these are two two-wire sensors that we used to in this course. They have to be powered. It's only a two-wire sensor, right? So what does that mean? Well, this guy powers up through the load. So it says right here, it says, do not use sensor without a load. So if you hook this thing across the line, what would you do? As soon as you activated it, you would have a short circuit. And what would probably happen? Well, it would probably destroy the sensor, right? So these guys probably not blow up, but it will definitely destroy it. These didn't blow up, but and we talked about this, and some of the things we're going to have to measure are some of the things that's going to be in the data sheets. That when you replace these things, you might not replace it with the same sensor, right? You understand, but you have to make sure that the sensor you replace it to has either the same or better specifications. And this is an inductive sensor, which means this guy's going to sense what? Metals, yeah. So some of the things we're going to have to measure. Here's our proximity sensor. And then, of course, the standard symbols for electrical controls. is just a limit switch, right? So it's a open, and then we come out. And if I come over and did that, what would happen? Yeah, mess it up, right? So this guy's going to actually power up through the load. If this was a 24 volt sensor, it would have to be a 3-wire sensor, but this is running off, sorry, and this will be our load. What could it be? It could be a what? It could be a relay, it could be a light bulb, it could be a lot of different stuff over there. So when we measure across this thing, normally if I was to come over here and have a normally open push button, and then I close the push button, what voltage should you expect to measure across the push button with it closed? Well, let's say 120 volts. So what would I measure across the push button when it was closed? Guys, how much resistance does a closed push button have? 0. Okay, so voltage drop is equal to V, right, times what? I, let's say 20 amps, times 0. How much voltage does a closed switch drop? None. If it's good, it drops 0 volts. How much does the fuse drop? That drops. Well, it drops, right? How much does this drop? How much does a good fuse drop? Pretty close to 0. A fuse will have to drop a voltage because it takes a voltage to blow it, right? Understand? So if we go and the lower the current rating, the more resistance it has. The higher the current rating, so I've seen, a 1 milliamp fuse maybe have 100 ohm resistance, but that's at 1 millivolt, 1 milliamp, right? So if we measure across, it still is going to drop 1 millivolt, right? You understand that? So fuses drop a little bit of voltage. So, but when we measure across this, if it's got to power through the load, and when this switch right here closes, it's got to power through the load. So these guys are going to drop a voltage, right? You understand? I think ours drops between 4 and 6 volts because it's got to have power, right? Does that make sense? And it's power through the load. But still, if I've got 120 volts over here, now, that still leaves me, what, 116 volts or 100 and well, that would be 114 volts, which is still plenty enough to power a 120 volt load, right? You understand that? So these guys are going to drop a voltage. So we're going to get into trouble using a lot of solid state 2-wire sensors, because if I came over here and tried to put another one in series, what would happen? It's going to drop an additional 4 to 6 volts. Now we're dropping 12 volts, right? You understand that? So we have to come up with some type of scheme on solid state sensors where you can't use you don't usually use multiple solid state sensors in series if they power through the load, because they have to drop a voltage, right, even when they're true. Everybody okay? Does that make sense? So we're going to have to measure that. We're going to measure currents. If you look at the lab, what's some of the measurements we're going to have to make? So a very simple circuit, inductive sensor. So that's what we got to know, because in motor control, we're on experiment 1. You didn't get a 1? Huh? We got 1, 2, and 3. We got three labs. No, that's not the lab, but that's the introduction, right? Yeah, those are not labs. That's just a discussion. So we're going to measure the voltage across when it's off. We're going to measure the voltage across when it's true, the voltage across the load when it's off, the voltage across the load when it's true. But it's going to be less, right? We're going to measure a voltage drop across this because it's a 2-wire solid state sensor, which means it's got to power through the load, right? You understand that? In electronics, since we always deal since we always deal with tolerances, we call it the 10-to-1 rule. Have you ever heard of that? Have you ever heard of the 10-to-1 rule?
Maybe your class we probably heard and can't remember.
So if I came over here and had a 1K ohm resistor, and I had it in series with a 10K ohm resistor, basically for approximations, we could ignore the 1K. Because why? It would only cause, we got 5% resistors anyway, right? And they could be high or low. In a parallel circuit, just for approximation, guys, if I came over here and I had a 1K ohm resistor in parallel with a 10K ohm resistor, for an approximation, which one could we ignore? Not in a parallel circuit, because it's always small. Your total resistance is always smaller than the smallest, right? So for approximation on a parallel circuit, we can ignore the big one, right? If it's a what? If it's a 10-to-1 ratio, we call that the 10-to-1 rule, and just for approximation. So that's basically what we're kind of doing here. We're ignoring the resistance of the what? The solid state sensor, because why? Because it's a lot. But if I was to come over here and put another 1K, then I couldn't ignore the 1K anymore, right? You understand that? Because now it's above the 10-to-1 rule. And this is for approximation, and it makes your life in electronic circuits a lot faster, because you don't have to deal with a lot of resistors and calculate currents and voltages and all that kind of stuff. And you'll still be close enough, right, to understand. So if you could tell if the circuit was working or what, not working. But we have to be real careful when we try to put these solid state, 2-wire solid state sensors. Now, when we get into 3-wire solid state sensors, the voltage across is going to be a lot less. And why is that? Because it's 3 wires. They're not powered through the load. They're powered individually, right? So they don't have to develop power. So we're going to measure that. What else do we have to measure? What else are you going to have to measure? Not we. It's you. We're going to have to measure current, which means we're going to have to do what, guys? We have to break the circuit, right? Everybody okay? Now, this is where people blow their fuses, because they set their meter up for current, and they get current measurements, and then when they make voltage measures, they forget to do what? Back voltage. So y'all need to be careful here. So we have different currents we're going to measure. And this should have been explained. So holding current, I don't forget, leakage current, holding current, and this will be explained in the data sheets. So be careful here, because you could, this is where you might blow the fuse in your meter, right? And each one of you should have your own meter. Then we're going to come up and modify the circuit just a little bit and add a what? Now, usually how many contacts does these solid state sensors have? 1. What if I need more? What if I need more contacts off my sensor? Not off my sensor. My sensor's only got 1. We will what? We would add a control relay. How many contacts can a control relay have? Oh, yeah, a lot. Probably, maybe not as much, right? You understand that? So we could use the sensor to pick up a control relay, and then that's a control relay. So that sensor probably can't provide enough current to run a what? Motor starter, not a motor starter. So what can we use? So we can use control relays to control more current, or we can use control relays to get more power, right? You understand that? So we can use control relays. I think we got the only control relay we have is a small. It's a 3-pole double throw. So what does the number of poles mean on a relay? The number of contacts that's being controlled, right? You understand that? And then double pole means each one of them's got what? That means they got 2 positions. Everybody understand that? So you got a normally open contact you can use, or you got a normally closed contact you can use. So we have 3 poles on this relay. So when you use these things, so these are quite a bit different, guys. So here, than motor controls, and we talked about this. Notice there's no little plate up here that shows you the pinout, right? Y'all understand that? So where are you going to look that information up at? In the data sheets or the book, the little book that we have in there. A lot of times on your control relay, you'll look and they'll have the symbols on the side, and then they'll show you the pinout also. So that's another thing you might start realizing, especially on little control relays. A lot of times they'll have the actual pinout on the actual relay itself. So you can see this is one. If it'll focus in, probably not. But this is one pole. This is one pole. This is one pole, and then down here, this would actually be the relay coil itself. Of course, these we should know. I've got a brown wire and a blue wire. The brown wire should be pointing toward what? L1, and the blue wire should point toward the load, which is going toward, right, toward the load. So the load is between here and L2. Everybody okay? Any questions on this? Now, these lab questions you're supposed to answer on your own, right? Okay, let's look at lab 2. Here we're going to move over to, this is still proximity switches, even though they gave it its own name. You don't have to wire the 3-phase motor for low voltage. It's already wired for us. So you can see the actual metal jumpers on there. Talks about direct scan. This is what we learned is through the beam. So both of those are exactly. So direct scan starts off true, right? Y'all understand that? And then the object it's trying to detect makes the sensor go what? False. And then we have retroreflective. Retroreflective, we have a retroreflector on one side. Then we have a transmitter receiver on the other. Here it works kind of like the through the beam. What advantages does retroreflective have over through the beam? Yeah, it doesn't have to be perfectly aligned, right? You understand that? So through the beam, you really got to align the transmitter and receiver up. Here, you don't have to be near it. So these guys are true when the object detect. And then when the object goes through and breaks the beam, then these guys become false. Then a diffuse scan. This guy actually depends on light being reflected off the objects. What do these guys have problems with? Well, all of them have trouble with glass. But you're right. It would have trouble with. What depends on the amount of light that gets reflected? Yeah, the color, right? So the lighter the color, the more reflection you get back. The lower the color, the less reflection you get back. And by the way, a retroreflective usually can be used as a diffused. So we'll use ours. A retroreflective usually can be used as a diffuse. You just don't put the reflector, but you'll find out the range is going to be a lot shorter. The one that has the longest range, by the way, is through the beam, right? Because you don't have to send light both ways, and you're not depending on reflected light. So this is the 3-wire sensor. So here we are going to connect. What's the connection? So I got a brown, black, and blue. So brown will go toward L1, blue will go to L2, right? You understand that? And then the black will go to the load. Are you okay there? Okay. So this is the photoelectric sensor. If we use it like this, then this. If I come over here and use this is the actual retroreflector. Which one will have the longest range, the retroreflector or the fuse? Yeah, because it's not dealing with color, right? You understand that? So yeah, we don't know how far it is. So we'll start off with the basic circuit and see the difference in the wiring. Everybody okay? And then we'll basically do the same thing down here, where we'll take it and hook it up to a motor starter and run a 3-phase motor. Everybody okay there? Any questions on that? You're going to have to measure the voltage when it's on, the voltage when it's off, across the load, right? When you measure between L1 and L2, you should get 120 volts. But what you have to understand, guys, is that we can put other control elements right on the L1 side. Can't put anything on the L2 on 3, but we could put other contacts and stuff on the L2 side, on the L1 side, right? You understand? And then the power actually comes on when L1 gets through to the sensor. Everybody understand what I said? That makes sense? So you're basically going to make the same measurements here, but we should find the voltage drop across this is going to be a lot less, and it's going to drop a voltage because it's solid state, right? You understand? It's not a closed switch, but we should find out it's going to be a lot less than that 4 to 6 volts it took to operate our inductive sensor. And we'll do the same thing here. Now let's take a look at lab 3. So any questions on that? Are y'all okay? So here, what you're going to do, oops, I need a new battery in mine. Here we're going to set up the basic part of a car wash, and everybody's been through a car wash, right? So, oh, no, most of us have. So we got 2 lights. We got a red light and a green light. We start off, the light should be what? Should be green, let you know it's ready to do what? Pull your car up there. We're going to go to a retroreflector, so this is something you got to remember. So this guy's going to be true, right? You understand? Until the car does what? Breaks the beam, right? Then the red light's going to turn on, and that's then we're going to keep it on for a certain amount of time. When we get there, we'll go over the timer. I don't think I brought the timer in. Make sure y'all understand that it's a programmable timer. A programmable timer means it serves almost any timer function we could possibly think of, besides on delay and off delay, right? But it's also referred to as a programmable timer. It's also called a contact control timer, which means depends on whether you're going to use it as an on delay or an off delay or a one shot or all different types of applications that we can do it, but we'll look at that. So what's going to happen is once the car pulls up, breaks the beam, the red light's going to come on, it's going to stay on for a certain amount of time, and then it's going to go off. And then that's as far as we're going to go. So we're not going to get into running everything else. So all we're going to do on this lab, and you're going to have to, your team is going to have to design this. We'll have fun with it. So lab 3 is a design project. It says the vehicle, let's see, the photoelectric switch used to detect the vehicle is in place and has reached the desired location. So we're going to use our retroreflective sensor, which is true. The output is true when the car is not present, right? Yeah. It's not green. We're talking just about, you're talking about the lights, I'm talking about the sensor. Before the vehicle is in place, the green light is on and the red lamp is off. When the vehicle is in place, the red light turns on to signal the vehicle to stop, and the green light turns off. And it says after the red lamp has been on for 10 seconds, it is automatically turned off, even though the vehicle is still in place. Green light remains off as long as the vehicle is in place. And we're going to use a programmable timer. But like I said, when y'all start getting to this lab, when the first group gets to this lab, then we'll stop and go over the programmable timer. But we have to put a watt on there. To occasionally test the red lamp to make sure it is still working because of a burned out bulb and prevent a vehicle from accidentally over traveling past the set limit, a push to test button is required that can test the red lamp when no vehicle is present. So that means you got to have a push button that does what? You can press and turn the red light on as long as the push button is pressed. So it's going to bypass the sensor. So what type of logic would that be? Or, yeah, or logic. Or logic, right? So either the sensor can turn it on or the push the test button. Okay? Good job. So any questions on this one? So here's the actual circuit, or the actual diagram. This is not the circuit. You'll have to come up with your circuit. So remember, we're using retroreflective because we don't have a transmitter receiver like this, a break apart. We don't have a through-the-beam sensor. All we got is a sensor that we can either use as diffused or we can use it as retroreflective. So here we're going to use it as retroreflective, right? You understand? And remember, a retroreflective is true until what? The car breaks the beam. So any questions on this guy? So any questions on the 3 labs? So what we do, all the sensors are on the back side or the second shelf there. Your group can go back and get one of these when you get through with the sensor. I don't want them stored underneath. I want them to be restored back over on the shelf. Everybody understand that? Any questions? Wait a second, let me. So we're going to be working on. So you're going to group up or pair off with somebody. And let's go lab.